So because of that, they show a spread of some too large values and some too small values. Okay. It can be both at the same time. That's the thing. Okay. Now, so then,
Salam alaikum.
all right. So then,
Sir,
yes,
sir,
yes,
my school ends at 5 p.m. Pakistani time. Can you move it the class to 5:30 at least?
no, not at the moment. It is very difficult. I have back-to-back classes. I'm really sorry about that. You should manage using your phone while traveling a bit, okay?
Yeah, mister. I can manage normally, but today I was like sick. That's why I was asking.
Yeah, no, it's very difficult because I have to back-to-back classes. I have to move to the class. Okay,
It's all
that's
right,
why.
sir. I'll manage.
Yeah. So it cannot be entirely eliminated, and it can only be reduced by taking average. Okay. So usually these two have certain examples as well. One of the examples for this part, like systematic, could be zero error, right? Zero error is when the object or the instrument doesn't start from the very start. It's either, shows you too large or too small value. And then this ones have like reaction time and obviously environmental effects. That could be the reason of random error. Okay. Now, so um, you can always find the actual value when you're doing systematic ones. And that is by if you use this formula all the time, like actual value should be equal to the measurement that you've taken minus the error. Now, this is the main formula. But now error can be obviously negative or positive. That depends on what kind of error you're looking at. For example, I just want to tell you that if you have the positive errors, and they could be like negative errors, and the positive errors are when, it shows a measurement too large, right? So measurement is too large from the actual value. So you obviously then you would just add the positive value in the formula. And if the measurement is too small, then obviously you need to add a negative error. For example, if the measurement was too small, right? You'd say, okay, I want to find an actual value, okay, of my clock that shows, a reading that is less than it should be. Then obviously you got a measurement of this, and the error in your clock was minus 0.05. So it would basically show you the actual reading would be 110. So the thing is that what we need to understand is that the formula will automatically change positive or negative sign depending on what kind of error is this. We just need to see if the error is causing a larger value in the measurement or a smaller value. That's what we should be on. All right. If you have any questions, please let me know. Hmm. Okay, Laiba, Yaya, everybody understands this, right?
Yes.
Yes, sir.
Yes, sir.
Okay. Now, the thing is that comes accuracy and precision. So, with accuracy, you can say that it's actually the of a measurement describes how close the experimental value is to the accepted value. So, what I mean by this is that you have 9.81 meters per second square as the accepted value of acceleration due to gravity, right? Now, you did an experiment to verify that, and one person got 9.71 and the other person got 9.00. So obviously that we can say this is more accurate than this one, right? Because it is closer to the accepted value. In any case, then the precision has two different, uh, say, definitions and depends on the situation, really. So, first definition is related to instrument. So, if the examiner is talking about an instrument, like for example, the examiner is comparing micrometer, screw gauge, and ruler. So, you'd say that it is the degree of exactness to which a measurement can be reproduced. So, what I mean by this is like if you measure thickness of a paper using a ruler and thickness of paper using a micrometer, then the ruler would give you
Sir, it is
value
degree of extraction.
exactness. Now, ruler gives you a maximum of 0.1 centimeter precision, right? But a micrometer, like let's write in millimeter, is 1 millimeter of precision, and in micrometer, it gives you 0.01 millimeter, like 100 times more precise. So that means that micrometer is a more precise instrument than a ruler if you're doing the same experiment with these two, okay? The other definition is related to the experiment. And in the experiment, when you've done it, so it depends on how close the readings are to each other. So, speaking of the same thing, now you have taken like one student got 9.81, 9.82, 9.84, and maybe 9.80. So because all these values are very close, so they're precise compared to somebody who got 9.74, 9.94, 9.84, and 9.64. So now, although both values are very close to the actual value, but these values are not very precise because all these values have a bit of, zero point 0.1 difference between them, right? Zero point 0.1, yeah. And those are very close because, they're like 0.01 differences between them. So experimentally, it depends on how close they are. Instrumental way, it depends on uh, at which degree it can reproduce, which means how many decimal places it can give you. So that's something you should remember. Okay, is that clear? Any questions, please? Hiba,
Yes,
Ayan,
sir.
Mad.
Yes, sir.
All right. Let me see who is not here. There's a lot of people who are not here today. And why is that? Not very happy about it. Okay. Aman is sick. Dua is clashing. Okay. And Kurbi is traveling. Ahmad. The other Khadija is not here. Javeria is not here. And Hiba is here, right? Hiba, you are also why have you like your name is also Hiba Bakar, right? Okay. Okay, that Hiba. All right. So the Zahan is not here. Oh my God. I'm going to kill that guy. Okay, now let's start. Let's start and move to the next part. Okay. So, like, we can also compare this using an analogy. For example, if you let me see if I did the analogy. Okay, no. So, the analogy is that if, let's suppose, like this is your target, right? So, this is your target. Let's make 4 cases out of it. And you fired 4 bullets and they land somewhere here, just right where your target is, right? So the thing is, it has an accuracy and obviously precision. So accuracy is very high in this particular thing. Okay. And the precision, because they're all close to each other, the precision is also very high. Now, if they land somewhere, away from the target, like in this case, so it means that the accuracy is low, but the precision is still high because they're very close to each other, but it's not close to the actual like accepted value. Okay. In a case where it does land close to um, like it does land close, but the values are a bit away from each other. In this case, we could say that the accuracy is high, but the precision is quite low. Wait a second, please. Oh, holy. Okay, so it is quite accuracy is high, but the precision is low. And if it's like this. So then we can say that this is like low accuracy and low precision, both of them, right? Now, I just want to tell you that when you make a graph of these situations of different trials that are happening, so for these trials, I just want to tell you for the first one, if this is the accepted value, right, then the graph would seem like this. The graph will have the peak exactly over the accepted value, like this, and the spread will be very small, right? So this is number of values. Okay. So in this case where it is like low and high, so if this is the accepted value, then the graph will just shift to one side. which means that it is not exactly on the accepted value. It's moved to the left or right because it could be higher or smaller than that. But because the precision was high, the spread was low. Okay. In case of accuracy is high and precision is low, so except the graph peak is going to be on the accepted value, but now the spread is going to be very large because the precision is low. So you have values ranging from very large to very big values. Okay. If it's not the case for both, then the accepted value, the peak might never form, peak will not form on the accepted value. And obviously, the spread is going to be large because it's low precision as well. Everybody understands this? So, generally, what you
Sir,
should
once
understand,
more.
yes, yeah. Generally, you should understand is that um, the thing is that accuracy means that peak of graph is on the accepted value. All right, is
Sir,
that
does it
clear?
have to be on the accepted value or it can be closer
Yeah.
to it?
Yes, yes. If there are no errors. Okay, so this is the accurate experiment. So peak has to be there. And precision would mean that there must be less spread. So the higher the spread, like in third and fourth graph, it has low precision because the values are ranging from very large to very small. They're not very close to each other. Do you understand this? Now,
Yes.
so the thing is, what makes it shift? All right. So generally, I would just tell you that if it's systematic error, then systematic error causes peak to shift. All right, because it could be too large or too small. And random error, which cannot be guessed, right, causes spread. Sometimes the values are going to be bigger, sometimes values are going to be smaller. Understood?
Sir, wait, the first two graphs are for high accuracy, right?
And first is high accuracy, high precision. Second is low accuracy because the graph peak is shifted, but the values are precise because they're close to each other. Okay.
Okay.
All right. Hiba, do you understand? Yaya, Ahmad, Suhail, Laiba.
Yes.
Okay,
Sir.
very good. All right. This basically this chapter needs a bit of teaching before we can really do anything. Anyway, so now rules of significant figures. These are very important. Please learn before we head on to uncertainties now. So first of all, you got 504. If they're like a non-zero number of both ends, then the number of significant figures are three, and you can write it as the scientific notation of 504 times 10 raised to minus 2, like that. Okay. Now, if you have a number like this, 54000, it means these all numbers are non-significant figure, only these ones. So up till, a non-zero number, it will be significant, which means it has two significant figures, only these ones. And you can write it as 5.4 times 10 raised to. You omit, when you're writing in scientific notation, you omit non-significant figures. Now, if you're given with 200, now 200 could be basically 1, 2, or 3. Now, depending on data, really, what I'm saying is that the series, there could be three series to this. Like, for example, if the series you see was 200 and then next number was 300 and 400, it means that now it shows one significant figure because only one number is changing. If the series of the next number were like 210, 220, right? 230. Now there are two numbers changing, like 2 and the next one. So it's two significant figures with respect to that. And if the series like 201, 202, 203, then it's three significant figures. So it really depends on what kind of data you have, right? So if it was one significant figure, then we just write it as 2 into 10 raised to a minus, sorry, 2. Do you guys understand this?
So for 504, how is it 5.04 times 10 to the power of -2? Won't it be positive?
Oh, I wrote negative. Sorry. Okay, thanks for correcting. All right. Anything else?
Sir, if
Yes.
if the significant figures are 2, so for the last value you would write 2.0 times 10 to the power of.
Yes, 2.0. That is correct. Okay.
Okay.
And if it was 3, then 2.00. All right. So then, in case the examiner gives you 2.200.0, automatically you should understand that he has put a 0 here for a purpose, which means he wants to tell you that all of these are significant figures. So it has 4 significant figures. And now you should write it as 2.000 times 10 raised to power 2. Understood? Otherwise, he's not basically writing anything in air. So he wants you to know that 0.0 means that you also need to include every value that is there before 0. Okay. Now, then it could be like 0.000305. Now, if there's a 0 in the start, and then no matter how many zeros are there, they're all non-significant. Okay. After the first one, then they are significant figures. So you can say there are 3, and you should write them as 3.05 times 10 raised to minus 4. Then comes 0.005900. Now, all these numbers, as the previous rule says, are non-significant figure. But if he has put like zeros intentionally after this, which doesn't make sense, why would he put it? He wants to put it because he wants to tell you that it's significant figure, so it has 4. And now you should be writing it as 5.900 times 10 raised to minus 3. Understood?
Yes, sir.
All right. Yes,
Yes,
very
sir.
important. Okay. Hamad and Yaya,
Could you pause here for a
Yes, sir.
second?
should I do what? Do you understand? Or should I
Yeah,
explain it again?
I just need
Okay,
to
very
copy
good.
quick.
Okay, please copy this. That's good. Okay. Now, you guys done? Should I go forward now?
Yes.
Yes.
Okay. Okay. Now, before we start uncertainties, I just want to tell you a small rule here. Okay. And this is like very, very important rule that you should write down right now. Oh my God, I hate this. Second, wait, sync. I think I'm gonna take. I'm just gonna explain um 2 values, and then we can move forward. Yeah. Okay. Fine. So the rule that you guys need to remember for writing answers is that for significant figures, always remember that always write the answers of calculations. Okay. So when you're calculating using formulas, etc., in least number of significant figures or one more than that. Okay. In your data. That's what you should always follow. So let's suppose in your data, they were like one value was given as 2 and one value is given as 3, and your answer came in like 5. So you should round it off to 2 or 3. So if one value is 2 and one value is 4, then okay, that doesn't make sense. Let me just give you a short example from this, right? Anyway, then the other thing that you should remember is for the decimal place. Now I'll just change the color so I have less space. So why did I put so much? I'll just change this to, let me just put it a bit below this. So I have more space. Okay. All right, I want to put it here. Anyway, now the other rule is for the decimal place. So for decimal place, just remember that it shows precision of the instrument. So decimal places must be the same as precision. So I'm going to tell you how. First, let's talk about significant, right? For the significant one, I would say that if, let's suppose, you have a value, you use a ruler to calculate a length, right? On the ruler, you get exactly 10 centimeter. Now, writing 10 centimeter would be wrong because the ruler has a precision of 0.1, so you should be writing 10.0 centimeters. So now it has the correct precision and the right decimal place. Do you guys understand this?
Yes.
Now, you also in your practical exam specifically, you calculate time using your stopwatch. Okay. So the stopwatch gives you a time of 5 seconds. I'm just assume no. Let me take it 3 seconds. Okay. Now, if your stopwatch, generally the stopwatch that is given in exam is 0.01 second accurate, right? So if you write 3, that would be wrong because you should be writing 3.00 seconds. Is that clear? Because you're like now uh, putting the right precision, whatever is reflected from the instrument itself. So you have to look at the instrument and check how many decimal places it gives. Understood? Now,
Yeah.
what you're going to do is, yes, yes. Now, what you're going to do is, Khatija,
Yes, sir.
that is not fair, you know.
Oh, I think I
Did you
turned it
forget?
off.
That's very bad, Khatija. Very bad. Now, suppose they ask you to find speed. So you know speed is distance over time. And then when you're finding 10 divided by 3, it should give you a number like 10 divided by 3. It should give you a number like 3.33333, right? So it's a recurring number. Now, how many significant should I write to get the answer right? So what I'm going to do is, I know that the minimum significant figures in my, oh my goodness, this app will be like, I hate this. Okay, never mind. So right now, if you see the minimum significant, the significant figure in this will be 33333. Now writing this will be wrong because now you have made the calculation, you have to check SF. So the significant rules say that the answer in calculation should be the least number significant, one more, which means this one has 2 and this one has 2 as well. Oh, sorry, 3 and 3. 3 and 3. So I can either write this as 3.33 or I can write it as 3.333. I cannot write it as 3.3 or bigger than 3.333 because the rule says that your answer should be minimum significant figure or one more than that. Is that clear, everyone?
Yes, sir.
Sorry, could you repeat?
Yes. So you see, in this particular part, what I just want to tell you is that, let me just move it even further down. So what I'm saying is that in this particular part, as you can see, that I have a reading that is coming as 3.3333 and so on, right? Is that clear?
Yes.
Now, my significant rule says that always write the answers in calculation, least number significant or one more than that. Now, this value that you see right here has three significant figures, and this value also have three significant figures. So this is my data, and the answer should be in the least or one more than that. What which means is that either I should write it as 3.33, that's three significant, which is the least number in my data, or one more than that, which is 4. Now, writing this as 3.3 would be wrong, and writing this as 3.3333 would also be wrong. Do you guys understand this?
Yes.
So whenever you're measuring something, check the precision. Whenever you're basically calculating, you have to check the number of significant figures. That's the rule of the business here. All right. You should always remember this. Anyway, now these two rules are very important in uncertainties as well because they will be used in uncertainties a lot and paper 3, which is a big part of exam. If you're failing on paper 3 in your school, make sure you practice it a lot because it's 23%. It can move your grade up and down. Okay. So make sure you put a lot of effort in your lab. Okay. Now, so moving to uncertainty, we'll just complete this section now and then we'll move to the way we do uncertainty tomorrow. And obviously, the questions are given already, so we can, do them. First of all, you should remember that when you're taking uncertainty of a reading, reading means that basically, if you're looking at a ruler, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, like that, right? 11, 12, 13, 14, 15, okay, and so on. So right now, it's 1 centimeter here and 2 centimeter here. Is it? Oh my God, no. It's 1 centimeter and so on. So what you should understand is that the uncertainty means that suppose I put something like this, align it with the ruler, but I put it here. So now I can only guess whether it's 0.4 or it is 0.5. So it's somewhere in the middle, though it's closer than 0.5, but I can't say it is 0.45 or 0.46 or 0.47. So it means this section is all uncertain. Is that clear, everyone? So generally, when you
Yes.
take the reading of this sort, what we do is we see this and we say, okay, it's between this. So we take half of it like this. So if you're taking reading, like reading at a point, then you say that, all right, the uncertainty, the uncertainty is half. Okay, while it is doing this, I should put a charger already. Never mind. I'm just, trying to, I don't know what did this show this. Okay. So, so remember, whenever you're taking the reading, the uncertainty is always equal to the half of least count. So in this case, which is a ruler, the uncertainty will be 0.05 centimeter, because that's how, you say it's 0.45 or less than that. So that's how we take this uncertainty in the reading. But now when you take measurement, so you don't know if the two values, like you read twice, so you add both of them. So in the measurement you say the uncertainty is always equal to the least count, because the measurement in reading means you're taking two values and subtracting them, so errors add up. So it means for a ruler, the uncertainty will be 0.1 plus minus means bigger or smaller, this 0.1 centimeter. Do you guys understand this? Now, in your exam, for example, you've been given in the lab, you see the stopwatch. Usually, a stopwatch will be there. Let's talk about voltmeter this time, okay? So, suppose on your voltmeter, you're doing an electricity experiment, and you see that your readings are 5.05, right? So this reading is coming on the voltmeter. Now they ask you what is the uncertainty in this, especially in question two, where they say, okay, estimate the uncertainty. So the uncertainty in this would be basically 0.01 volts. How do I know this? Because this is a measured value and I'm going to check the last decimal place for it. So the minimum error it can cause would be 0.01. Do you understand this?
Yes, sir.
Like that. And you can, do it for all of the instruments like that. So you have to check the least count. Whatever the least count is, that would be the same uncertainty in the instrument. So that's just an example of two things that I wanted to make sure that you know. All right. So we are going to stop here because tomorrow we have a very important topic to cover. That's uncertainties. And then hopefully you'll understand this chapter. It's not very hard, especially for paper two and paper one. It's just very important for paper three that your lab teacher should tell you about, and you should focus in lab. Okay. All right. Any questions, please go ahead.